Section 2.5, precise definition of a limit. So we have what is called the Epsilon-Delta definition of a limit. And this is the most precise way that you could possibly describe what's going on. We talk about x is getting arbitrarily close, the y values are getting arbitrarily close to our limit, what we call our limit. Well, here's the definition. Let f of x be defined for all x except possibly at a, so x not equal to a, over an open interval containing a. Let L be a real number. Then the limit as x approaches a of f of x equals L if, we're going to focus on this quite a bit, for every epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus a, the distance from x to a, is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. So the epsilon is how close we want our y values to be to our limit. The delta is how close the x values are to what we're approaching. X approaches a in this case. So this is going to be very general, but most of our arguments are going to follow the same structure that I have here. Our focus on this last sentence is going to be, 1, let epsilon be greater than 0. We do not know what epsilon is. We are saying it's a positive number. Now, it's assumed that it's going to be a very small number. In a couple of places we'll need to point that out. But let epsilon be greater than 0. Choose a delta equal to something. Okay, we will figure that out, usually as we go, maybe even from some scratch work. So start with absolute value of f of x minus L, and then we will simplify that expression using our value that we've chosen for delta. In the end, we want to show that the absolute value of f of x minus L is less than epsilon. Now, our scratch work is these two. Our scratch work is going to be these two steps. We're going to usually on the side sort of manipulate that expression until we get something less than epsilon. We will always have some scratch work. There's this quote that says, the proof is simple, but it won't fit in the margin. That is from a famous mathematician. A lot of these are not going to be difficult. However, getting the proof, doing that scratch work is where most of our real proof, the meat of it, is going to come in. So let's go ahead and look at a couple of examples. Prove that the limit as x approaches 1 of 2x plus 1 equals 3. Now, from our earlier sections, we know that we can evaluate this at 1 because it's a polynomial. We've said it's continuous. If we evaluate that, we get 3. Look at that. Okay, so we want to show that this is definitely true. So we will begin with let epsilon be greater than 0. All right, next we will choose. We kind of want that to be readable. Choose delta equal to something. Right, so that the absolute value of x minus 1 is less than delta and it's greater than 0. That's coming from that definition of this. Now, consider the absolute value of f of x minus L. Now, from here on, it's going to look a lot like what our scratch work would be. Okay, so I'm just going to go ahead and include it in here instead of using several pages for this. My scratch work is actually going to be contained in this. So if I take the absolute value of f of x minus L, well, my function here is 2x plus 1. My limit that I'm proposing is 3. So if we manipulate that a little, that'll be 2x minus 2. Okay, now I want to get an x minus 1, the absolute value of x minus 1. So what I will do here is factor out a 2. And what I want in the end, so somewhere over here, I want to say this is less than epsilon. So this is going to prompt me to say, actually let me put this over here, 2 absolute value of x minus 1. If I want that to be less than epsilon, that means absolute value of x minus 1 is going to be less than epsilon over 2. That is my choice for delta. So going back over here, I'm going to say choose delta equal to epsilon over 2. Now, hopefully we'll see what happens there. This won't be equal to. This will be less than because x minus 1, the absolute value of x minus 1 is less than delta. Well, which means that it is less than epsilon over 2, which is then equal to epsilon. So what we have shown is that absolute value of f of x minus L is less than epsilon, which is the last line right here. And if we look back at our definition, that is what we want to end up with. So therefore, we can then conclude the limit as x approaches 1 of 2x plus 1 equals 3. We've just finished our first epsilon-delta proof. All right, let's look at another that's very similar to this. Prove that the limit as x approaches -1 of 4x plus 1 equals -3. Again, what we've said before is we can plug that in. We can evaluate at -1, and that is, in fact, -3. But now we want to prove that in general. So let's let epsilon be greater than 0. Choose delta equal to something. We'll do some scratch work to figure that out. Speaking of which, I don't want that in my proof. All right, we want to choose delta so that the absolute value of x plus 1 is less than delta. Why plus 1? Because our limit is -1. Okay, so it's the opposite there, just like it was earlier. Our limit was as x approaches 1, so we used x minus 1. All right, now consider absolute value of f of x minus L, which is the absolute value of 4x plus 1 minus our limit is -3. So I'm going to go ahead and just say plus 3 there. And that would be 4x plus 4. Just like before, here's my scratch work. 4x plus 4, the absolute value, I want that to be less than epsilon. Factoring out my 4, we have a common theme there, which means x plus 1 must be less than epsilon over 4. There is our delta. Epsilon over 4. Now, for these linear problems, we will have just epsilon over something. That's usually how these play out. All right, so factoring out the 4, x plus 1, which is going to be less than 4 times epsilon over 4, which equals epsilon. Therefore, the limit as x approaches -1 of 4x plus 1 is equal to -3. All right, let's move on to one that's a little bit more complicated. We have a quadratic here. Prove that the limit as x approaches 2 of x squared equals 4. This is going to begin the same way. Let epsilon be greater than 0. Choose delta equal to something so that the absolute value of x minus 2 is between 0 and delta. All right, consider absolute value of f of x minus L, which in this case is the absolute value of x squared minus 4. Now, I cannot just take out a constant here. That won't get an x minus 2 in here. However, what I can do is factor this. And because of the absolute value bars, I get x plus 2 times the absolute value of x minus 2. Okay. Now, this is where the complication comes in. I have an x plus 2 and x minus 2. I happen to know, and I'm going to do a little bit of scratch work down here, I happen to have that x minus 2 is less than delta. All right, well, that means x minus 2 is between delta and negative delta, once I drop the absolute value bars, which means that x plus 2 is between delta plus 4 and 4 minus delta. Okay, I'm going to change that just a little. Let's make that minus 4 minus delta is less than x plus 2 is less than delta plus 4. I've actually lowered my lower limit, so that is perfectly fine. Factoring out a negative here, Okay, x plus 2 is less than delta plus 4, which means the absolute value of x plus 2 is less than delta plus 4. Well, I cannot choose a delta that depends on the value of delta. That really doesn't make any sense. So what I'm going to say is I would really like it if delta was less than 1. Just say it's less than 1. We want to restrict it there. All right. So if delta is less than 1, okay, so if delta is less than 1, then that means that x plus 2 is less than 5. All right. I'm going to use that value of 1 and that value of 5 in this a couple of places. So I'm going to assume, we assume that epsilon is less than 5. So that delta is less than 1. And I'm going to actually use epsilon over 5 up here. I'm going to use that limit I have. And I don't have to choose 5 like I think we used 5 last time. No, we didn't. It was epsilon over 4. Okay. We will use 5 again, but it's not completely a coincidence, but it's just the choice that we made. Okay. Since the absolute value of x minus 2 is less than delta, okay, which is epsilon over 5, and the absolute value of x plus 2 is less than 5, those two numbers do coincide. Absolute value of x squared minus 4, which is the absolute value of x plus 2 times the absolute value of x minus 2, is less than 5 times epsilon over 5, which is equal to epsilon. Therefore, my limit as x approaches 2 of x squared equals 4. Now, I made that statement that delta is going to have to be less than 1. There's something I can do to actually make this work in general. Scratch this. I can say I want delta to be the minimum of 1 and epsilon over 5. That would guarantee that it's actually less than 1. And so that I can actually take this statement out. All right, there we go. Now this next one's going to be very similar. Again, it's a quadratic, so quadratics tend to have a certain form to them. Prove that the limit as x goes to negative 1 of x squared minus 2x plus 3 equals 6. Again, let epsilon be greater than 0. Choose delta equal to something with 0 less than absolute value of x plus 1 is less than delta. Consider absolute value of f of x minus L. So this is going to be x squared minus 2x plus 3 minus 6, which is going to be x squared minus 2x minus 3. Now perhaps you might notice that I've got this. I might be able to factor this. Let's go ahead and factor that. And then we'll consider it a little more. X plus 1 times x minus 3. So one of these two factors, I know it's going to be bounded by delta. All right, so let's go ahead and mess around with that just a little bit. We know that negative delta is less than x plus 1 is less than delta, similar to our argument previously, which means x minus 3, that would be subtracting 4, and negative delta minus 4. Now instead of lowering my lower bound, I'm actually going to increase my upper bound. So this would be delta plus 4. And this, if I factor the negative out, delta plus 4. So that the absolute value of x minus 3 is less than delta plus 4. Now, I can actually choose 5 here because, just like I did previously, I could choose 5 because I could just say delta is going to be less than 1 by restricting my epsilon in some way. I'm going to go ahead and do that. We'll just do that. All right, so let's go ahead and choose our delta so that it is the minimum of 1 into epsilon over 5. Actually, the same choice we made earlier. That will then make this less than delta, which is less than epsilon over 5. We know that x minus 3, or switch that. Yeah, no, that's right. Epsilon over 5, and x minus 3 is less than 5 because delta is less than 1, which is equal to epsilon. Therefore, the limit as x approaches negative 1 of x squared minus 2x plus 3 equals 6. All right, we're going to take a trip down memory lane for this next one. We have got a limit law here. The limit as x approaches a of f of x equals L, and if the limit as x approaches a of g of x equals M, then the limit of the sum of the functions is the sum of the limits. We sort of took this for granted at the beginning of this chapter, so let's actually go ahead and prove this. Show you how this works. So first, I have two assumptions. I have these two assumptions. Well, the first actually means that if epsilon is greater than 0, or for all epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. And similarly for our g of x. So I want to go ahead and let epsilon be greater than 0. Let epsilon be greater than 0. Now, since I have an epsilon greater than 0, I'm going to go ahead and say there exists a delta 1. I'm actually going to have 1 for each of these. A delta 1 such that if the absolute value of x minus a is less than delta 1, then the absolute value of f of x minus L is less than epsilon over 2. I can actually get it as close as I want. Now my choice of epsilon over 2 is not arbitrary because in the end I'm actually going to add these two so that it comes out to be less than epsilon. Right. So similarly, there also exists a delta 2 such that if the absolute value of x minus a, and I need to make the restriction that we are greater than 0 as well, is less than delta 2, then the absolute value of g of x minus m, absolute value, is less than epsilon over 2 as well. All right, so I have a similar statement for both of these. All right, now I want to make a choice here, and hopefully this will be clear why I do this in a second. But let delta equal the minimum of delta 1 and delta 2. So this will guarantee that actually both of those conditions hold. I need to make sure my x and my a are close enough to actually keep both of those conditions. All right. Consider the absolute value of f of x minus g of x, or plus g of x, minus L plus M. That is what we claim here. Now that is equal to the absolute value of f of x minus L plus g of x minus M. All right, now we have something called the triangle inequality. Triangle inequality, which actually says that the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. So this allows us to break this up into two absolute value statements. Okay. Now, since delta is less than, or let's just go ahead and say this, since the absolute value of x minus a is less than delta 1, and the absolute value of x minus a is less than delta 2, let's actually move this over here. Let me make sure I include that. So since both of those things are true, this means the absolute value of f of x minus L plus the absolute value of g of x minus M is less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. Therefore, limit as x approaches a of, we don't need an absolute value there, f of x plus g of x equals L plus M. And there we have proven one of our limit laws. Now we can actually do the same thing for other limit laws. Just happen to choose this one because it's one we use quite often. All right, now we have two more examples to go. The first of which is proving that a limit does not exist. Okay, so this is actually going in the opposite direction. We want to choose an epsilon and actually find our delta. And then we have one that will be limit from the left or the limit from the right. So that one's very similar, but this next one is going to be a little different. So the way that the definition works for a limit existing is for every epsilon greater than 0. So for it not to exist, we have to say there exists an epsilon greater than 0. And so it starts in that way. So the way we're going to do this is first say choose epsilon equal to, and for this I'm going to do exactly like they do in the book and just choose epsilon equals 1/2. All right, then we need to find a delta so that we're actually greater than epsilon. So it's sort of, we're going from the opposite direction, okay? Choose an epsilon, a specific. Previously we had a specific epsilon, but it was unknown, okay? It was just a number. Here we're going to choose a specific one and then find a delta so that we are greater than or equal to epsilon. The exact opposite of that. All right, so let's let delta be greater than 0 and our limit, okay, greater than or equal to 0. All right, and I'm going to choose an x value actually, and I'm going to have an x equal to negative delta over 2. Then absolute value of x minus 0 is, well, negative delta over 2 minus 0, so that my absolute value is delta over 2, which is less than delta. Okay, so I have an x value so that my x minus a, since notice that the limit is x approaches 0, so that my x minus a is very close, but I want to show that the y values, the outputs, are bigger than 1/2, that I'm going that direction. So let's take the absolute value. Okay, so but the absolute value of f of x minus L, okay, equals the absolute value of x over x minus L. And since my value of x there is negative delta over 2, that is going to be negative 1 minus L, which is going to be equal to 1 plus L, because our L is greater than or equal to 0, and because my L is bigger than 0, this is going to be greater than or equal to 1/2, which is greater than epsilon. So I've shown that no matter how, if I can find an x value where I'm close to 0, that I still get a y value that is going to be bigger than my particular epsilon. All right, now this is if the limit is greater than 0. So what if the limit is less than 0? Then we're going to use x equals delta over 2 instead of negative delta over 2. So let's show that the absolute value of x minus a, in this case 0, is less than delta. Well, that is going to, again, equal to delta over 2, which is less than delta. But the absolute value of f of x minus L, go ahead and jump into that. Okay, minus L. And if my delta is delta over 2, then that is equal to absolute value of 1 minus L. Now, because of our triangle inequality and some other facts, this is equal to the absolute value of L plus 1, which is greater than or equal to our epsilon because it's 1/2. So no matter what our limit is, so the way I want to conclude this is for all L, the limit as x approaches 0 of the absolute value of x over x does not equal L. Now, if you recall, this is actually a function that is positive 1 when you are greater than 0, and it's negative 1 less than 0. So the limit at that point does not exist. We knew that, but we were proving this in general. All right, our last example, definition, a limit from the left and the right. The one thing I want to point out here is that if we are from the left, if we're coming from the left and the right, we don't have absolute value bars around our x minus a. So here, the distance between the two is just going to be positive, meaning we're coming from the right. Our x values are bigger than where we're headed, the limit from the right. And the limit from the left means that our distance between these two, x minus a, is going to be negative. That's the big difference. So for this one, we're still going to do let epsilon be greater than 0. Choose delta equal to something so that 0 is less than absolute value of x minus, or not the absolute value, because we're coming from the right. X minus 4 is less than delta. Now, this would be a good place to do some scratch work. So let's take the square root, so the absolute value of the square root of x minus 4 minus 0. I want this to be less than epsilon. So that is the absolute value of square root of x minus 4. All right. Well, this happens to be the same as the square root of the absolute value of x minus 4. What we really want is that x minus 4. So if we square both sides, the absolute value of x minus 4 is less than epsilon squared. That will be our delta value. Whoa. Squared. That will be our delta value. So we'll choose that to be epsilon squared. Now consider, okay, and I want to ignore my scratch work. Pretend that didn't just happen here. Consider the absolute value of f of x minus L equal to the absolute value of x minus 4, the square root of that, minus 0, because that is our proposed limit. which is equal to the absolute value of the square root of x minus 4, which is equal to the square root of the absolute value of x minus 4. But wait, the absolute value of x minus 4 is going to be less than, the absolute value is definitely, but that means that the positive version of that is less than delta. But our delta is epsilon squared, so this is less than the square root of epsilon squared, which equals epsilon. Therefore, limit as x approaches 4 from the right, the square root of x minus 4 equals 0. All right, that brings us to the end of this section. As always, I would suggest you watch some of these more than once. See if you can, follow the reasoning. That's the big idea. And this is something that, by the way, I don't expect you to regurgitate. If anything, I want you to be exposed to this, because this is the sort of rigor and the preciseness that mathematics is really all about. And people have been working for a long time, hundreds of years, to make things this precise so that we always know if what we're saying is true. That's really the big idea. All right, that's the end of this section, precise definition of a limit.